And so for most projects, we'll get a virgin stress state, but then there'll also be some rotations going on. So we're showing both a left lateral rotation, so SH max is rotating counterclockwise, or a left lateral rotation, and then there's also a right lateral rotation. And we see that phi is being reduced from 0.36 down to about 0.33. So we can estimate kind of what that stress changes when you have these interferences, as well as directionally where they actually located. We're seeing that these left lateral rotations tend to be more on the left side of the wellbore, and the right lateral rotations, in this case, tend to be on the right side of the wellbore. And that goes back to kind of this theory that I was showing before, whereas when you're initially fracking like a well 1, and then you go into well 2, that's off to the right, we would see SH max kind of rotating to the left in between. And similarly, if you have the opposite sort of scenario, you see a right lateral rotation off to the right. So these things are also dependent if you're treat a well above and below, we would see these things kind of wrapping around the previously treated well. So what do the fracture characteristics look like in these different scenarios? I've got the virgin stress state colored blue, that left lateral rotation orange, and the right lateral rotation right. It's showing that in the virgin stress state, you primarily have higher dilation tendencies, so these fractures are dilating the most. So when you have these stress shadow effects, you're not dilating the fractures quite as much. And how does that translate into fracture volume? We have a lot higher fracture volume associated with these virgin stress states. In this case, they're primarily dip slip. So we have the dip slip events are dilating a lot more, whereas these rotating stress states with these strike slip events, you're creating a lot less volume. In fact, it's almost going to zero, and so it's as if you initially create some fractures, they open up as dip slip, and then if you reactivate them, now they're just slipping and strike slip, and we're not really creating any new fracture volume. And but they could be kind of bigger in seismic moment. So it could be, we're basically saying, not all microseismic events are created equal. That we have to be able to successfully interpret that data to understand it really well. And in this case, the strikes are all really staying similar, whether you're in the virgin stress state or reactivating some of these other fractures. It's just how they're failing and how they're open. So one thing that we like to do is if you have a lot of data, say you're looking at a number of stages that are all being treated the same, we can stack all that data on top of one another or reference them all to their stage center. That gives us a much clearer picture of what a single stage might look like, and then we can create some of these heat maps to kind of get more of like a picture of how to move forward and how to plan on what your frac would really look like for future wells. And so that's what I've done here. I've stacked all the data on top of one another, and I've got these 3 different scenarios. And what I'm showing is that these colors are showing stress shadow effects. So we're looking at those breaks, whether they're normal dip slip, and that would be shown here as cool colors, which are representative of the virgin stress state, versus are they strike slip and they're turning red in this case. And so we're showing 3 different scenarios, and I'm saying these stress shadow effects, which are shown here as red, are time dependent. So they'll be there, and then at some time they're going to go away. And so there's ways that you can take advantage of the stress shadow effects if you're aware that they're happening. So the first case is showing stage lag, or this DT of 0 days. The second one is a rapid stage lag, like a zipper frac, where the stage lag is 0.2 days, and then this long stage lag where you're waiting 18 days between when you've treated the wells. So what does that look like? This box is kind of where you'd expect your frac to land. It's defined by your average stage spacing, so this is how big your stage would be, versus your average well spacing. And the contours are showing how we model proppant from that injection, and these dots are showing where the perforations are located. So this is an isolated case. We see all the cool colors right around the wellbore, indicating not very much stress shadow effect. There's no other wells being treated. Your fluid pretty much goes out from the perforations and mostly stays in zone right around the stage you're treating. And then in this example, they've treated wells offset by about 900 feet, so over here, and then they treated this well over here, also offset by about 900 feet, and then they treat the center well after 0.2 days. And what we see is that stress shadow effect is very evident on the offset wells. This is showing SH max in the virgin stress state about 80 degrees with this left lateral rotation and right lateral rotation respectively on left and right side of the well. And so what's going on is the proppant model responds by saying your proppant, your fluid, which is most likely it should be being contained between these high pressure areas. So you have this high stress area, and your fluid and your proppant is really trapped in between that pressure, that high stress area. Versus what happens when you treat, in this case, this is a depth view. This is the top of the Wolfcamp and the top of Wolfcamp B. We treat this shallow well, and then nearly 18 days later, they treat this lower well. We see all cool colors indicating there is no more stress shadow. The stress shadow has gone away. Now when you inject into the lower well, all your fluid is going back to the previously treated well. So you're just sending fluid back to the fractures that you initially created on the shallow well. And we can create graphs to understand what's going on there as well. So what we're doing is we're tracking where the virgin stress state events are. Where are the events that are that fit this virgin stress state? We're not worried about the altered stress state. We're just saying where are the virgin stress state events, since those are likely indicative of microseismic events that are occurring in unpressured up rock, and that pressured up rock is going to prevent your fluid from getting further out. So where are those virgin stress state events? Well, when your stage lag is low, they're located, this is perpendicular distance from your stage center, right around the stage you're treating. Whereas at some point, that stress shadow goes away, and now all your virgin stress state events are going very far laterally, going off to previously treated wells. And that's also the case in the vertical sense. They're initially low stage lag, they're right around the wellbore, and then once that stress shadow has gone away, in this case the shallower well was treated first, so those virgin stress state events are going back to those shallow wells. So kind of in conclusion, these stress shadows develop around previously treated stages and wells, and they'll go away. And you can either take advantage of them or not. But if you don't take advantage of them, they could be pushing your frac all over the place. And we can do these stress inversions, figure out what that virgin stress state is, and solve for the virgin stress state, as well as understand where areas have already been pressured up and where you have these high stresses. So with that, I'll just kind of end. If you want to learn more, we have a booth here. Annalise is right here. She's our salesperson for MicroThermal Energy. So thank you. Yes?
Is there questions left?
Yeah.
You know, I think I might be kind of out of time.